importance weights based on the maps of the samples, the locations of the samples, and the current observation. We will go into the details how this weight update looks like. And as a result, you get a weight update. So every sample gets a weight. And then the observation is used to actually update the map of each sample, because it's a new observation. And I now say, okay, the pose of the robot is here. Given the pose of the robot was here, I can actually update my map. This is exactly what happens. I do a number of small, tiny EKF updates for every landmark individually, and then obtain a new belief for that system. Yes, please.
Do I do that for every particle? This update of the whole map?
Yes, exactly.
Isn't that pretty expensive? And we could say, okay, like in this example, particle 3 is pretty far away from what we observed, and so we just calculated for the first 5 particles with the biggest weights.
So first of all, it's absolutely right. You need to update the map of every individual sample. So if you have n maps to update, that's obviously up to n times more expensive than a single map. That's true. However, if you compare to the EKF, the great advantage that we have here is that we have individual 2x2 Kalman filters. So this is a kind of a constant time operation for every landmark. We typically observe just a small number of landmarks. This is done very, very efficiently. Compared to the EKF, where we have to invert our huge m by m dimensional matrix, which is actually a more costly operation than this operation here. Of course, it depends on the number of samples. If you have whatever trillions of samples, the more samples you have, the more costly this operation obviously gets. But for reasonable sizes, this is not a limiting factor, at least for large maps. If you have a small map, the EKF may be more efficient, but if you have large maps with a large number of samples, this makes a big difference. But again, just to stress this, a substantial number of research activities in this area says, okay, how can we reduce the number of samples in order to be more efficient? So it's an absolutely valid question, but from the computational complexity point of view, we actually gain something if we do it in that way, because we only have low-dimensional EKFs and not one large high-dimensional one, and therefore I can typically easily compensate, given that the number of samples is typically constant and the number of landmarks is typically larger than the number of samples that I have. Yes, please.
So do we have a threshold weight where we say, okay, this particle is so unlikely now, we just skip it and create a new one? Or?
No, that doesn't happen at all. So okay. There's no threshold which eliminates a sample. The resampling process kind of takes care of you for that, because it draws samples proportional to its weight. So if you have a sample which is a very low weight, there's a very small probability that it is drawn and taken to into the next generation of samples. So this comes automatically just by drawing with a sample with a probability that is proportional to its weight. But it's not that we need to maintain an explicit threshold to eliminate the samples. This is not the case. Okay, any further questions? Okay, perfect. So what we have now done in the first half an hour now is kind of give you a rough idea how the EKF works. And everyone would probably, the FastLAM works. And every one of you is probably saying, okay, I think I understood that. And that's perfect. I hope that this is the case. We will dive now a little bit deeper into the math, but it should not violate the picture that you generated in the mental picture that you generated of FastLAM right now. The only thing is what I will now do, if we dive into the details, I want to give you more detailed explanation why something is exactly as it is. So for example, this thing, how is a weight exactly computed, what we have here? Why is a weight like this? So I would kind of, after this more informal introduction to FastLAM, I would now go deeply into FastLAM and say, this is the result, or this is a design choice, and this design choice leads to these and these computations, which then result, for example, in this way of computing the importance weight. And that's kind of my key idea, that after this lecture, you're actually able to implement such a system yourself. That will be my goal. Okay, let's look to the key steps of FastLAM, and we look into so-called what is FastLAM 1, which is kind of the first, obviously, first generation of FastLAM. There's a second generation of FastLAM. But what I explained here is something which is known as FastLAM 1. What it does, it draws samples according to the standard odometry model that we used in localization. So it says it extends the path posterior to the next point in time by just taking every sample, and for every sample I draw the new generation according to the motion model. That's exactly the same as in Monte Carlo localization. So this first step should be kind of clear. Anyone who needs a short recap from that, how this works? Perfect, good. So we take our old generation of samples, and for every sample we draw a new pose taking into account the odometry information. This gives us a new sample. The second step is to compute an importance weight, and the importance weight mathematically is defined as a target divided by the proposal, and it tells us how do we need to correct our belief as this guy over here, the odometry, is not the full distribution that I want to approximate, so my target is just a part of that, because I want to take into account as well as the observation. And this is something which comes in here. And so what are the individual elements here? So this is a Gaussian distribution. And what it says, it takes a current observation minus the expected observation or predicted observation. And this predicted observation is computed for every particle. As every particle has its own map, every particle will come up with a different expected observation. Compared to the EKF, where I computed one expected observation, I compute here an expected observation for every sample, because every sample keeps its own map. So for every sample, I say how well does the obtained observation match with the expected observation, and I have a measurement covariance. The measurement covariance is something which I also used in the EKF. This takes into account the uncertainty of the landmark itself and the uncertainty of the observation. It's kind of this part in the EKF which gets inverted, this part which I need to invert in the prediction, in the correction step. That's exactly what's called the measurement covariance. Then the third step is just a belief update using the EKF update rule. No black magic in here, and the standard resampling operation. Okay, so let's now dive into the detail. If you want to implement that algorithm, how does this look like? I start with my FastLAM1 with known correspondences. Again, that was something we assumed. We have n samples here, ranging from k equals 1 to k equals n. So we iterate over all samples. What do? Okay, let's say we have our individual samples. So every sample has a pose and a landmark estimate. Therefore, it's kind of a list of landmarks and an importance weight. Okay, and we have that for every sample. So for every sample, we have the current pose estimate, the weight, and a list of 2x2 Kalman filters, given a mean and a covariance, which represents the poses of the individual landmarks. This is what this guy should express here. So the first thing we do, we say, okay, given the current pose at time t minus 1 of that particle, and the odometry command ut, I sample a new pose for that sample. Standard odometry motion model sampling as in Monte Carlo localization. Okay, first part was easy. This is a prediction step. Now let's go into the correction step. Okay, we assume J is kind of the feature that we observe in our current observation. This is the state association variable, which tells us just the current measurement that we take is actually particle landmark J of that particle. Same as in the EKF. Okay, again, as in the EKF, I have to distinguish two situations. First, the landmark has never been seen before, so I need to initialize it, or it had been seen already in the past. So I start with, it has never been seen. What I do is, I compute its mean with the inverse of my observation function, exactly in the same way as this was done in the EKF. So if I've never seen a landmark, I use the first observation to initialize it. I compute the Jacobian, I compute its initial uncertainty, taking into account how certain am I about my observation, and the Jacobian, and I have a default importance weight, standard value, because otherwise it would be undefined. Because, so this is a new landmark.